Okay, today we're going to look at certain models that follow the exponential curve as they grow or as they decay. Here I've pulled up examples of the number of COVID 19 cases in four countries: India, US, Brazil, and Mexico. Um, just glancing at the curve and recalling what the exponential curve looks like shows you that these cases have been increasing exponentially with different slopes for each of these graphs. But nevertheless, they have been increasing exponentially. Now, the question is, what kind of natural phenomena gets modeled by something that is exponential? So we are essentially working in reverse here, because remember, we have data about this virus and how it spreads. We can plot the data, and we can make an educated guess about what the graph looks most similar to. And we know it looks similar to an exponential function. But at the other end, we also want to understand that what kind of phenomena gives rise to an exponential growth. So it turns out that whenever the rate of change is proportional to the quantity, we have exponential growth. For example, population. How fast a population grows depends on how many people are already present, right? Or if you think about how radioactive material decays, how fast the material decays depends on how much of that material is there to start with. So any natural phenomena which grows or decays according to how much there is called or is can be modeled by an exponential function. So saying that the rate of change is proportional to quantity is like saying dp over dt is proportional to p for some quantity p, or dp over dt equals k times p, where k is just a limit of proportion or a constant of proportionality. Sorry. This can be rearranged as dp over p equals k dt integrated to get log of p equals kt plus c, or p equals e to the kd plus c. Now, e to the kt plus c can then be rewritten as e to the c times e to the kt, where e to the c, I'm going to relabel that as p naught, where p naught equals the constant e to the c, that's the population or the quantity p at time 0. So in general, these kind of functions always look like number or constant e to the power k times t. One of the applications is Newton's law of cooling, which is if you take an object at a particular temperature and leave it in a surrounding which is of a different temperature, then how does the temperature of that object change over time? An example of this would be refrigeration, air conditioning, etc. So Newton's law says that the temperature of object at time t is given or depends on this relation, that the rate of change of temperature over dt over t is k times t minus t sub s, where t sub s is the temperature of the surrounding. Example. Let's say there's a bottle of water at room temperature, 70 Fahrenheit, refrigerated in a fridge where the temperature is 44 Fahrenheit. After half an hour, the temperature of the bottled water is found to be 61 Fahrenheit. Find a model for this scenario. So we can use Newton's law of cooling, which says that dt over dt is k times t minus 44, where 44 is the temperature of the surrounding, which is the fridge. Because remember, the water is being put in the fridge, so that's a new surrounding, which has a temperature of 44. Now T0 we know is 70 Fahrenheit, which is the temperature of the bottled water right at the beginning. We do a little change in variable. Let y equals t minus 44, because dy is then dt, and y0 is going to be t0 minus 44, which is 26. So that my differential equation now becomes dy over dt equals k times y, which is dy over y equals kt, which looks very similar to what we had in the previous page. We get y is lambda times e to the power kt. Now there are two constants here, lambda and k. We got to figure out both of them. Let's start with lambda. We know by definition that lambda is y naught, or y at 0, because when t is 0, e to the power 0 becomes 1, so you're left with lambda. But we already know that y value at 0 or at time equals 0 is 26, so that lambda is 26. So we get that the general equation yt is 26 times e to the power kt. But we recall that t is actually y plus 44, so it becomes 44 plus 26 e to the power kt. Now we're still left with finding the constant k. To find that, we know that half an hour later the temperature is 61, or T at 30 is 61. Plugging that in, we get 61 equals 44 plus 26 e to the power 30 k. Subtracting 44 gives me 16 equals 26 e to the power 30 k. Log of 16 over 26 equals 30 k, or k is 1 over 30 log of 16 over 26. So the temperature at any time t is given by the relation 44 plus 26 times e to the kt, where k is this particular number. Now, this is a procedure you can follow for any problem that stems from a cooling or a heating in a surrounding temperature which is different scenario. Basically, any situation that uses Newton's law of cooling. Right. Okay, that's the end of this section. So we've learned about exponential functions, their derivatives, inverse of exponential functions, logarithms, their derivatives, applications, and models. Next up, we're going to be studying a few more class of functions. So the reason we are doing these functions is in order to broaden the number of functions we can work with. Because later on in the course, we are going to be learning tools. Before we learn the tools, we want to learn all the objects that we can work on. So we are just building vocabulary on new kinds of function at this point.